request each one of you, feel free to engage Professor through the Q&A session, and Professor will be able to address most of your questions. So feel free to engage Professor on the questions that you feel that you'd like him to address or to guide you and be able to progress well. For now, I want to give Professor an opportunity to take us through today's topic on AI on malaria prediction. Welcome, Prof.
Thank you very much, Prof. Dennis. Welcome everyone to this session again. I hope you can see my screen now. Okay, so today we are going to talk about explainable AI for malaria modeling. And we welcome you to our AMNET machine learning group. So today we want to talk about one of the modern techniques in machine learning, in artificial intelligence. And I want you to practice along. Please, if you have your laptop there, please, you can follow me and practice along as I demonstrate it. Now, if you have not heard about explainable AI before, or XAI for short, it simply refers to a set of tools and techniques that are used to make the behavior of machine learning more interpretable. That is, when your machine learning predicts, we don't just stop at prediction, you go further to know why the machine learning model is predicting what it is predicting. So that is one new technique that you must embrace. And so when you use these explainable techniques, it becomes more, the result becomes more interpretable to humans, such that we'll know why this model is predicting what, which features are responsible for this type of prediction. So essentially the goal of explainable AI, we usually refer to it as XAI, is just to clarify how and why a machine learning model or an AI model makes certain predictions. And it helps to ensure that both experts and not experts can trust the model effectively. And then it makes it useful for getting insights in real-world applications. We're going to show you the applications in malaria modeling or malaria data analytics. Now, in malaria modeling, for instance, explainable AI can be used to explain why a model predicts high malaria severity in revealing which symptoms are really responsible for the severity. For instance, in our data, we have symptoms like vomiting, jaundice, or fever, Coca-Cola urine, and so on and so forth. Why? How are they influencing the prediction of either the patient will have severe malaria or non-severe malaria? So by increasing this model interpretability, explainable AI will help us to bridge the gap between complex AI models or techniques and actionable insights. Now, let's see the types. There are various types of machine learning explainable AI. We have the sharply additive explanations. I'm going to share this code with you later. I'm going to consider two major types today: the sharply additive explanation, sharp, we call it sharp from game theory, sharply additive model explanations. So we call it sharp. Sharp. And then that's number one, sharply additive model explanation. That's number one. Then number two, we have line, local interpretable model agnostic explanation, line. Number two is line, local interpretable model or agnostic local interpretable model agnostic local interpretable model agnostic explanations. Model interpretable, local interpretable model agnostic interpretations. Okay. Now, let's see these methods one by one. This one is line. Okay. So we're going to see these methods one by one. So today we are going to consider sharply additive model explanations. Sharply additive model explanation. In fact, they do it this way, this capital P, explanations. In fact, this one is small e, so that's where we got the name sharp, S-H. In fact, this one is also capital, sharply additive model explanation. And this is a popular method in games theory, where they will see the features as players in a game, and then the prediction is the payout, and then the features will go to the direction of the prediction they favor. So we're going to get there. We're going to demonstrate it in real life. We're going to see the practical aspect of it. So let's go to the practice now. Let's go to the practice. Now, let's see our usual code. Before you apply these methods, you have to know your usual code, the one we have done before, the machine learning, the codes, the caret and all that, the one we have done before. You have to have used your machine learning model to predict before you now apply these methods in order to understand the prediction better. Okay, so the first thing to do is just to load all your required libraries. So we have all these here. If you have not installed, please install them. I'm going to give you this code. It's nothing so different from the ones you have before, but just few changes, few additions. Okay. Now, if you have not done that, you have to do this, load your libraries also. Load libraries, required libraries. Okay, so let's see the libraries of these packages we have loaded, we have installed. Now, the data we are using is this malaria data. That's the only data we have so far. It's a published data. If you want to get the data, is here in this link. It has been published in Data in Brief. It was data on malaria patients of about 337 patients in one clinic in Ede, in Osun State, Nigeria. And there is a very interesting data. We're going to see what is in the data. So if you run it this way, you'll see what is there. Okay, here it is. You can easily view the data here. You see it contains age of the patients. Look at the number of patients. Look at this. 300 and what? Yes, it's still loading. It's still loading. Yes, this is 337 patients. Look at the age range of all the patients, different age range, right? And the other features there are sex, that is the gender of the patient, male for one, maybe 0 for female. A fever, if you have fever, yes, 1, no fever, 0. Cold, you have cold, 1, no cold, 0. These are symptoms. You have rigor, 1, no rigor, 0. Like that, like that. Look at all the symptoms. Sometimes you have malaria without bitter tongue. Sometimes you have it with bitter tongue. So all these are to predict whether the patients have severe malaria or not. That's the target variable.
We can't hear you.
So that's the target variable. Okay. Now, we will see how we'll use these data sets now. So the essence of the research question is to know which of these symptoms will really favor severe malaria or non-severe malaria. And by the way, this target variable is a binary variable, which is either it has severe malaria or non-severe malaria, 0. Okay, so let's see how we can use this data set. So the dimension is 337 by 18. And then we have the first few rows of the data, the names of the variables in the data, we can see. These are the names. And then if you like, you can attach the data so that it can recognize it. I've attached it before, that's why it's showing red. Then want to summarize it and then maybe see if it has missing data or not. This data is so good, doesn't have any missing data, missing values. Now, I want to exclude age. If you look here, you'll see that age is the first thing, is the first feature here. I feel it's different from others, although sex is also not a symptom, but I just left it. If you like, you can exclude it also and see how it behaves. But I want to exclude age in this particular study. So let me exclude and see. Now age is no more there. It has reduced to 17, but this is the target variable, okay? Now, let me do the feature plot with this. I want to see how each of them relate with the target variable. I want to see the distribution of each of them with respect to the target variable. Here we'll see using this code. This code may appear complex, but it is not complex, right? You can use that code to plot the relationship of the features with the target variable in the data. Okay, now let's see the variable, the data itself. Now we want to rename it, not severe and severe. We want to say, tell R, when you see 0 in the target variable here, 0 is not severe, 1 is severe. Then give it that nomenclature, and then we plot the target variable just to see the distribution of the target variable. You can see that the data is imbalanced. Number of people that seem to have severe malaria in the data frame is much more smaller than the number of people with non-severe malaria. Okay, so there are things to do about that. Now let's go into carrots. Let's go and work. We're going to do something about this. We talked about it later. Now let's see the carrot package. You can see it has a lot of it has a lot of models in it that we can use. I'm going to demonstrate with some models. You can see naive Bayes, you can see neural network, you can see multinomial model, you can see multilayer perceptron, you can see mixture discriminant analysis, you can see linear vector quantization, and so on and so forth. A lot of models that you can use. Current is so wonderful, but we can pick from these. We can pick few of the models to demonstrate with, but I'm going to try the first 2 or 3, and then I'm going to allow you. I hope you have your laptop there. You can ask questions and you can demonstrate by yourself. Today, we are going to demonstrate. I'm going to share this code with you, and then I'm going to allow you to demonstrate by yourself. It's not going to be difficult. Now, let's go. Remember the steps we are taking. The first one is to prepare your data, preprocess, clear your data, visualize, split your data, and all that. Already, we see that our data is clean, and then we don't need any form of feature engineering. Well, then we can visualize using the code I specify there, and then you split your data. I'm going to split my data very soon. Then we'll define the training control for cross-validation. We explain what cross-validation means, which is a very important aspect of supervised machine learning. Then you train your models. So we're going to train the models using carrots. Then we evaluate our model with the test data from the splitted data. Then we'll tune and resample as the case may be. Then I want to add number 6. We explain the model. We implement explainable AI today. So let's go for that. Let's go for it. Now, let's partition the data. Let's partition the data using caret, create data partition. Using caret, create data partition. Okay, so we have partitioned into 70-30 divide. You use 70% to train and 30% to test the model or to evaluate the model. Now we'll set seed for reproducibility, and then we have our train control. Now we are using, let's start with cross-validation, the tenfold cross-validation, the simplest one, just tenfold cross-validation. If you're not satisfied with your model, you can go ahead and try more, use repeated cross-validation with tenfold with 5 repeats, and then you can do different sampling methods, and then you can use hyperparameter tuning right here. You can use random hyperparameter tuning or grid search hyperparameter tuning, and then you can change the trait control of your model as the case may be. And this is what I would love you to do. I hope some of you have your computers ready. This is what I would like you to practice today. Today, I don't want to talk so much. I want you to decipher this. Don't be afraid to make mistakes. Even me, I still get errors. I still get error. You can see sometimes I get error. It's not as if those codes won't run, but to save time, you can just ignore and rerun again. Later it will run, or you debug your codes later. So we want to debug together. Debugging and getting errors is part of learning. If you get errors in your code, don't run away. Don't give up. Keep at it. Stay there. Work on it until you are able to debug and get that code running. Now, let's start with logistic regression model. In fact, that's what I want to start with today. So this is the typical way of doing the logistic regression model. So the first thing you do is to tell R or tell caret the target variable. Don't mind the spelling of malaria here. That's how it was in the data. You can change it from the data. The target variable, tell it the target variable. Then use this symbol. You are telling caret, please train this model for me using the method GLM and the data train it on the train data. Don't mind that this train and this train are the same name. Don't be confused with that. This one is a function, and this one is the name of the train data. If you like, you can even change this one to training. You could change this one to training. It will still work. You can change this one to training so that it won't confuse you. It will still work. But let's leave it like that. So the method GLM, then the train control, the cross-validation is very, very important in supervised machine learning to be able to cross-validate your model. So the cross-validation is this. So is this one we have specified here before? Okay, so let's have it. And this tick box, this tick is the same thing, is just to get the time it will take for the model to run. You can see. So let's have it. Okay, let me run the control first, and then let's run the model. Okay, so let's predict. Okay, let me see what is happening. Let me do it from the beginning. Maybe there are some libraries have not run, you can just run it. Sometimes it gives that kind of error. You can just restart, perhaps because it's not restarted, or you just try to run it from the beginning. Okay. You can see that one did not run before. It's running now. Okay. So let me run it. Okay. So now let me run the model. The data partition, the train control. Now you can see it has worked. So once you get that initial error, don't run away. Don't be afraid to say, oh, my model is not running. Oh, my code is not running. No, you have to be a man. You have to be courageous and stay there. What is happening? And then you keep at it. So now it's working. Now we are using this test data to predict and evaluate the model, this model. We're using it to evaluate the model by predicting with the test data. Now, how do we know the performance? We need the confusion matrix, which is also a function in Caret. All you need to do is just to supply this prediction that you have here into the confusion matrix and make sure that this test data, the target variable of the test data is also a factor, and then tell us the positive class, and then make sure that you have mode everything there, and then you have it. Okay, then you print your confusion matrix or your predictions. Okay, so we have it there. Look at it. This is the confusion matrix. This is true negative. It has flipped it. Not severe, not severe. That should be true negative. And this is true positive, actually. And then this is not severe, but severe. That's false positive, and so on and so forth. So that's the confusion matrix right there. And from this confusion matrix, you can get accuracy. Accuracy is the diagonal, the sum of the diagonal divided by everything, the sum of everything in the matrix. And that's what gave us this, right? And then we have the true negative rate. This is specificity, yeah, and this is true positive rate. The sum of this one divided by everything. And then, so we have our specificity, sensitivity, specificity is high here. And then we have our recall, which is the same thing as sensitivity. And then we have our F1 score, which is the harmonic mean of recall and precision. And then we have the balanced accuracy, which is the average of sensitivity and specificity, right? So we have a lot of results here just for one model. So you keep at it, ensure it's showing you that the positive class is severe. So you ensure that you have all these things in place, and then you get your model. Then you may like to plot the confusion matrix. That's it there, just to show it in the plot. Then the feature importance. So here is saying that EDIC, logistic regression is telling that EDIC is the most important feature that could predict malaria. So, but we want to see, out of all these features, we don't just stop here. This was where we stopped last time that we met, last month. But we don't just want to stop here. We want to see which ones out of all these variables are driving towards positive, towards the positive class, which is severe malaria, and towards the negative class, which is not severe malaria. So we're going to see another type of plot that would distribute these features. You see, it's just like playing a game. To say, if you are responsible for severe malaria, go to the right. If you are responsible for non-severe malaria, go to the left. Because actually, what we are predicting is not severe versus severe. So why is this one? What are the features that makes up for this one? And what are the features that makes up for this one? That is what we want to do here. So that's why we have the sharply additive explanations. This is what I was telling you the other time. So sharply additive explanation is one of the ways we will use, one of the methods that would help us to know the contributions of each of the features to the prediction. It helps us to know how much each feature contributes to the prediction made by our machine learning algorithm. And then essentially what it is telling us is that how do we determine, is a way that provides how to determine how to distribute credit. You know, when we say this model is predicting true positives, so number of true positives. These are the features that are responsible for that prediction. These are the features that we should give credit to. These are the important features we should take note of. These are the important variables that the doctor must take note of, not just saying these numbers are true positive, but what are the exact features? That's why we call it explainable AI. Which feature should we give credit to, for the model's output across all input features? Now, let's see the visualization. We're going to visualize these sharp values very soon, and then we're going to see how to interpret them. We're going to see how to interpret them. So let's see what we can. I'm going to see how we can interpret them. Now, let's see the visualization of the sharp plot, which will help us to understand not only the features that are important, of course, it will also tell us the features that are driving the predictions for the individual cases, the specific features. We're going to see that very soon. Now, what we should do is to, assuming the LR model that we have already trained, let's do that for the logistic regression that we have already trained. So we're going to convert it to a predictor object as follow, and then we're separating the target variable from the features. Now, let's see this. We'll call it a name, predictor LR. So we're going to say predictor. This is a function, actually. This is a function. Predictor new, the new predictor of this model. Then we are giving it the data, which is removing the target variable. What this is just doing is removing the target variable from the data frame, just separating it. Now, let's select a single instance from the test set to explain. So I'm going to replace 1 with the index of any other instance if desired. And that is what we did here. And then we call it X interest, X underscore interest. Now, the time is here to compute the sharp values for the specific instance. So let's compute now using this function called sharply new, right? So we'll predict, and then we put it based on this prediction we have made. So you can see everything is looped into one another. So you cannot do it in isolation. It has to be chronological. Now, that is it. That is it. We have computed it. And then we have it there. We can now visualize. Look at the values. Look at the ones that are featuring, that are favoring which ones. So we can see not severe, and we can see severe here, not severe, and then severe are the 2 labels. And then we will see. Let's visualize it to be able to understand it better. We're going to understand better. Now, just use ggplot to visualize. Now, here we go. You can see, essentially, interpretation of this is this, not severe, severe. You can see, it's saying that vomiting is you can see it will, if it is going towards the right direction, look at it on the number line, 0 here, minus here, positive here. If it is any variable is going towards the positive class, it shows that that variable is favoring the positive. Any variable going towards the negative line, it shows that that's a variable favoring negative for this non-severe. And then for severe, you can see the ones that are most prominent, and it is symmetric in nature. That's one of the characteristics of this sharply value. You can see it is symmetric in nature. The ones that are pointing this way here will point this way here. Can you see? The one that is pointing this way here will point this way there. Can you see? So that helps us to explain better or visualize better. This is a kind of plot you can put in your analysis or in your paper to be able to explain better what you are doing, which variables are important, and especially specifically to which class or which output label. So let's see how we can replicate this. Okay, look at this. So now, what is the interpretation of this? Each feature, you see, it has its own sharply value. I hope we have been able to study it, have been able to look at it, take a moment to look at this plot. Look at that. So it is now your turn. I'm going to ask you to practice. I'm going to ask you to practice now. So you can see, let's see, each feature has its own calculated sharp values, which was calculated in context of all the features. Now you can see the bars, the magnitude of the bars, which indicates the impact of the prediction. Now, rightward and positive. If it is going rightward, that is positive. It is favoring the positive class, which is severe. If it is going leftward, then that particular feature is pushing the model, prediction towards a negative class, which is not severe. Now, you can see that we have been able to explain better which features are pushing towards which. And you must understand that larger absolute sharp values means that the feature has stronger influence on the prediction. And then the ones that are close to zero indicate that the feature has minimal influence on the prediction. That's another way to view it. Look at the larger values, the ones that are tall, the bars that are tall. You can see it has positive influence. Like beta tone, you see, you can see. And then the ones that are just short like this, they don't have so much values. They don't have so much on that prediction. So that is what we are doing here. And we have just considered sharp values. Next time, we'll consider line, local interpretable model agnostic explanation. Now, we want you to now practice. I want you to try for other models. If you are there, I'm going to hand over to you. I'm going to give you the space to try. But before you do that, let me just show you how to do. Maybe for instance, let's do for random forest. Let's do for model like random forest. Then I'm going to allow you to try for maybe naive Bayes, KNN, bargain, decision tree, and so on. So let's start. I'm going to allow people to try and share their screens today. So if you have your laptop there and you are bold enough, I want you to prepare. We're going to give you the floor. So let's take it from here, or let's take it from here. Yes, let's take it from here. So let's call this one number 1, actually. So we're going to be able to put together 5 models today, at least. Okay, so just look at the way I'm doing it. So just do it. So we want to do for which model now? Random forest. Okay, train the random forest classifier. Okay, train the random forest classifier. So let me just call this one RF. Just call it RF model. You just change it. Just be changing it. Wherever you see logistic regression, just be changing it. So here now, we're going to say RF, just simply RF. Train control is still the same train control. In fact, if you like, we can use the train control here. Train control here. The train control here. Let's use this one. The one we had here. Let's change it. I can change it and run it. Let me run it. Okay, I'm just changing it. Okay, So I just want to demonstrate it, then I'll pass this code to you, and then you are going to try it. Okay, so let's look at it. So I said number 2. Okay. Okay, good. So now you are going to just copy the same thing. This is where we started from. We are using the same trade data and test data. This is where we started from. This is number 1, logistic regression, and we did the Shapley value. And then we have the results. And then we were able to interpret. So I'm doing it again for random forest. So let me call it random forest. Random forest. Okay. So change the name of the model, the same train data, then the control that we have specified, then change this one to what? RF predict. Sorry, we can use small letter, RF predict. You can use any one for the variable name. You can use capital here or small here, doesn't matter. Then what are we changing this? It has to be the same name as this. So RF, the same way it is written there. The same thing. Then instead of LRCM, I'm going to say RFCM. Then the same thing, I'm going to say RF read, which is the same thing here. You can see is hierarchical. Then I'm going to have the same thing all through. Yes, everything remains the same here. If you make any mistake, it won't run. So RF here, then the same thing, RF here. Okay, so don't forget the confusion matrix, RF confusion matrix, and then the variable importance of what? Of our RF model. And when we get here, we'll also have predictor RF, predictor new, RF model, same thing, all true, okay. Then we have what again, anything to change, Shapley RF, and then this one also RF, yes. All things being equal, it should run. So I want to plot Shapley RF. That's it for a single instance in what? Random forest. Random forest model or classifier, random forest. So we are going to do for KNN, for naive Bayes for me today. And then I'm going to see how you can work, you can do it. Okay, that's it. Let's go. Let me now run it from here. Let me run it from here. So actually, this is number 2. So you're going to do 3, 4, and 5 for me today. Okay. Okay. Let's see if it works. Remember, we changed the method here to RF. Okay. Okay. So let's see. It's still busy. This is showing that it's still busy. This red thing here. Okay. So you see that.
Hello. Good day, Prof. Sorry, Prof. If you are talking, your mic is muted, sir.
Oh, I'm so sorry. Hello? Hello? Oh, sorry, you were not hearing me. So we're going to look at what we can do. I'm going to allow you to practice this now. I say we're going to stop the video soon. Sharing soon, and I'm going to allow you to practice. So this is how I was able to replicate it for random forest. I want you to do the same. Just copy all the codes there and change the names to the model you are working on, the models and the method, the name you are working on. So I'm saying you're going to do for naive Bayes, you're going to do for decision tree, you're going to do for maybe neural net, and let's make it up to 5. I want 5 people to try. We have KNN, and then we have maybe one more. Let's see, maybe SVM. Okay? So please, let's try this now. Let's try these codes for these models now, if you are ready. So I'm going to stop sharing. But before I stop sharing, I want to take 1 or 2 questions before we now allow you to do hands-on and practice. Over to Professor Dennis to coordinate the questions.
Thank you, Prof, for a nice presentation. I now ask participants to ask questions or clarification to our good professor. Anybody with a question, kindly? Feel free to direct your questions to trainer